Good afternoon, everyone. It is my great honor to introduce Professor Nico Orce for his colloquium talk today on quantum correlations in nuclear physics. Let me remind you a few lines from his biography. Professor Nico Orce is a nuclear physicist driven by a passion for cutting-edge science and meaningful transformation. He has authored more than 150 publications, primarily in fundamental nuclear physics, with notable work also in top mathematics, biology, and astronomy journals. His research spans the nuclear chart, combining experimental techniques and theoretical methods to uncover new types of collective excitations and shell phenomena in nuclei. His recent work with collaborators revealed changes in nuclear polarization that refine the reaction pathways for element formation in stellar explosions, potentially explaining the universal pattern of elemental abundances. Sorry, I sound very nervous, but I was running to come here, that's fine. As principal investigator, Prof Orce has secured over 50 million rands in research funding. He has led pioneering African-led experiments at CERN and spearheaded major infrastructural research projects locally, including the GAMKA spectrometer at iThemba labs and the modern African nuclear detector laboratory, Mandela, at UWC. He's actively involved in research at iThemba labs, as well as TRIUMPH, CERN, and SOLD. He chairs the Tastes of Nuclear Physics conference series, he organized the 2013 Science Research Open Day. In 2012, he hosted Nobel laureate Serge Hiroshi at UWC. Professor Orce is a referee for most nuclear physics journals, associate editor of Atomic Delta and Nuclear Delta Tables, Elsevier, and an honorary visiting professor at the University of York. He has delivered talks at CERN, Yale, Cambridge, and Oxford, and has nominated for the was nominated for the Margarita Sales Award in 2021. Now you see, I've explained to you why I am so honored to welcome Professor Nico Orce, and we really look forward to your talk on quantum correlations in nuclear physics.
Thank you. Thank you. Hey, so I'm going to see that we are going to use this pointer, which I found first at CERN, has a little advantage because you can point on the screen and at the same time it points also over there. And you can do it vice versa. I believe you can point on the screen and also points on the computer. As you can see, it's both ways. And it's really what we need for this kind of seminars, you know. So I'm going to give you a talk which is a little bit complicated. You know, each slide here is like maybe a presentation by itself. So it's difficult to give this kind of talk. So I apologize if you don't get it, something, but you can ask me later, you know, because it's going to be difficult. But the fundamental idea here is to try to uncover some of the secrets of the quantum realm by measuring properties that we can measure macroscopically, by the quadrupole moment, matrix elements, lifetimes, things that we can actually infer atomic masses from the microworld and that can provide information about the microworld, about the quantum mechanics. These quantum correlations is what I'm talking about. So, yep. So the abstract, I changed it a little bit just to be more precise. But basically, we are going to be dealing with the many-body problem, which you may know is the problem of all problems, you know, because no one has been able to to solve it because it's practically intractable both mathematically and computationally. Right? The dimensions of the problem go exponentially, and it's very difficult to handle. And in this talk, I will focus on published work, our work that we have done through the last years mostly, and they include experimental methods to deal with this problem. So say the nuclear force, the nuclear potential remains unknown. No one knows the nature of the nuclear force, so we cannot excite the nucleus through the nuclear force. So we're going to be using experimental techniques like Coulomb-excitation reactions that gently excite the nucleus without invoking this nuclear force which remains unknown. So we are going to tackle the problem with measuring properties that they are known to us without, as I say, having into consideration the nuclear force. So we are going to infer new macroscopic variables from quantum correlations that could only be calculated through large supercomputers. So we're going to go the shortcut and say, okay, I don't want to know what supercomputers can do in 20 years' time, 30 years' time. I want to do a little bit of thinking, and we are going to try to figure out about the macroscopic world otherwise, with new ideas that we're going to present today, and they are published elsewhere. So we're going to kind of invent physics to determine the dipole polarizability and triaxial of the formation in general of nuclei. And we have performed different ab initio and shell model calculations that we are also going to present during the presentation. And at the same time, I am going to present you with the different research infrastructures that we have built, we have developed during the many years here, 15 years, to tackle these problems now and in the future, right? We have, as I say before, we have been leading science at CERN with research proposal, experiments, yield measurements, design of detector plates and chamber of electron spectrometer, which is now being commissioned at CERN as we speak. We have brought the GAMKA spectrometer, which was at the time, and even now, the largest grant ever given by the NRF, 35 million rands. So that was commissioned in 2021, right? So that was approved, or the funding was approved in 2018. The project started in 2012, October. So we are talking about 13 years in the making. And only this Wednesday, we are running the full first experiment at iThemba Labs, right? That's what it takes to make these things happen. We are handling big and complex data from these large gamma ray spectrometers. Here we have people who have developed sorting codes on how, the particles get Coulomb-excited, and then you need to Doppler correct them. We have Craig Mell, who did the MSc in developing a sorting code for these particular cases. And we have designed new laboratories at UWC and also at the University of Zululand, equipped with the fastest digitizers for quantum technology. We can apply quantum technology and apply the quantum entanglement to try to figure out whether we can recover some of the scatter particles, some of the scatter events that happen during the positron annihilation, positron-electron annihilation. And these are the things that we are working on. Of course, we also have nice high-performing computers, not very high-performing, but enough for us to run our simulations and minimizations of particle detectors and minimization of matrix elements. So all this combined is like a toolbox for us to tackle the problem, the mother and father of all problems. So I'm going to give you a little bit of an introduction to what we do. This is my YouTube channel. You Google nuclear physics lectures. I think this works better here. If you Google nuclear physics lectures, you can see that my lectures come first here, and then comes MIT second. So I don't know why, but it must be for a reason, So you can see now, if you go to the web page, you have lots of videos on nuclear physics lectures. There's about 150 videos, 80,000 views, 5.5 thousand, 5,500 watch hours, over 1,000 subscribers. I don't post much videos there since we stopped teaching and we stopped the Zoom teaching. But eventually we keep building up somehow, and eventually it will be nice to see how people have learned. When I sometimes I go to places, I go to University of York, and then suddenly someone comes, oh, I watch your videos, Prof. It was very nice to see that how to do the Nielsen diagrams or whatever. So as I mentioned before, we have led experiments at CERN. This is the web page where you can gather more information. We organize conferences almost every year. We have commissioned the Modern African Nuclear Detector Laboratory at UWC and at the University of Zululand. We have done experiments elsewhere, Coulomb-excitation measurements at Triumph in Canada, Munich, and here at the iThemba labs. And someone asked, as the bio, I have like 160 plus publications. About 1/3 of them are led by myself, or maybe by my student here, like Craig Mell, who just published a paper in Physical Review C about the large quadrupole deformation in neon 20, which agrees what we expect from this bowling pin nucleus, which is neon 20, is a formation of different clusters. And this is what the CERN is going to run an experiment this July, next month, to prove this in particular, that we have this bowling pin shape for, they're going to do that with low ion collisions. So far, CERN has been doing ALICE, high energy collisions. Now they're moving back to new physics with low ion collisions. And this is very timely right now. And we organize conferences, as you can see here. This is a Southern Stars conference happening next year, either at STIAS or here at Stellenbosch. We have to see that. And we are celebrating the scientific achievements of Dave Kilkenny, who is an astronomer here in South Africa, who has actually discovered new kind of stars, some brown dwarfs or pulsating brown dwarfs that he discovered with this telescope here. He still goes there. He's going to be 80 next year, but he still goes to Sutherland and go to the telescope and stay there from 6 p.m. until 8 a.m., whenever he has some observations. So these are the tough guys, which I like to see around me. That's why we go the extra mile to make a conference or to try to organize a conference for them. So this is the GAMKA spectrometer. GAMKA means or stands for gamma ray spectrometer for knowledge in Africa. As I explained, it's been a long process to reach where we are right now here. Lots of simulation, lots of science cases, lots of business plan, financing, procurement, over 1,000 financial operations to get this thing as the way it is. You have here laser alignment of the chamber or the frame. And here you have me presenting at the University of Paris-Saclay. And here we have some news stating that we actually commissioned this in 2021, but because COVID or whatever other things happened, didn't allow us to run the facility until this coming Wednesday. So there's a time frame here. We started in October 2012. I was chosen by the users at the iThemba Labs as the chair to lead this case. There was little hope to get 40 million rands. No one did it before. It's even worse if you come from UWC because you're not a leading institution. But there was a lot of opposition, but somehow we got it. We got the full amount given by the NRF. And in 2018, we were given the funds. Also, the University, Stellenbosch University is also part of, as you can see here, Stellenbosch University is also here. It's part of GAMKA. And it was commissioned finally in May 2021. And although we ran some experiments in 2019, then COVID hit, and then, load shedding or this and that, And until now is a very interesting time, very beautiful time when we are going to see all this work being put into action. So GAMKA is inspired by nature in a way that, as you can see here, it's the dandelion flower, which has like thousands of these florets clustered together. In such a way, the idea was to put as many detectors around, as many germanium detectors or gamma ray detectors around, so we can actually have a full coverage of any nuclear reaction happening at the center. In our cyclotron, at the iThemba labs, we have the 200 MeV cyclotron, the second largest in the world. So the idea was to have this array covering different angles to measure different things. And, this is a typical situation of us working in the evenings after doing the work at night. As I say, in the evenings, we have to, in the morning we do the typical normal work. In the evenings, we just have to keep going if we want to make these things happen. So this was presented also in Paris-Saclay by Sean Henricks. He presented a poster, I presented a talk, and the design is inspired on a concept by Elena Lori here. As you can see her, and Cobos and Elena did this GN simulation, and Sean is the design engineer who make this happen. And then we have all these structures that has to be strengthened because this was as you have more detectors, this has to be strengthened for the weight. So all these things have to be discussed through the nights and through many interactions. This work at iThemba Labs also allow us to help our colleagues at CERN, and we also manufacture some of the detector plates. We were flexible at that time, which can accommodate any kind of detectors, and also a chamber to accommodate the electron spectrometer, which is going to be commissioned very soon at the Solder Decay Station at CERN, where we have also experiments proposed. Last November, we ran a yields measurement, and Geneva here in the middle, she's analyzing some of the data from CERN. And that's what we are doing. We're still waiting for more beam time, but there's a long shutdown at CERN, and we don't know whether we can make it for this year. We have to wait another 2 years. But in the process, we keep investing at CERN and bringing people there and opening those doors. According to what we have built during COVID, we had to build something at UWC, and we built the modern African nuclear detector laboratory, which, as you can see here, has a very fast digitizers. These digitizers come from Cannes, from Italy, and they have to be approved by the Minister of Science there. Not everyone can have these things. There's another digitizer here, which they are used at CERN and at the iThemba Labs. We build new kind of detectors. This is an ionization chamber to measure the stopping powers. The beam goes through the target. We need to measure those very precisely to do our proper Doppler corrections of the gamma rays being emitted during the excitation of the reaction, the excitation of the nucleus. We build new chambers. We have plastic scintillators. We measure the calibration and the time resolution of these plastic scintillators, which we try to put at 180 degrees. We are creating our prototype, and the idea is to use quantum entanglement not only to get the right signals, but also the scatters in the detector. That's a very important point to gain resolution on that. When you are giving a positron emitter a substance, you get more interaction, more chemical interaction wherever you have a cancer, and this will help us having a much more defined picture, high definition picture, and at the same time with a very cheap technology, which are the plastic scintillators. Right here we have Elia building those plastic scintillators on site. and designing his own chamber to do all these kind of measurements, right? We have roughing pumps, we have turbo pumps, other chambers, and that's the idea to do in terms of quantum technology. We also support GAMKA. This is a typical silicon detector, double-sided, where you have rings on one side for angular distribution measurements, and you have sectors on the other side for Doppler correction. And then those are put together with the GAMKA spectrometer to do particle gamma coincidence measurements, which allows to reduce the background of otherwise, whatever you have in your room background, all the radiation that happen in the vault. Thanks to these detectors, we can do Coulomb-excitation, because the Rutherford scattering will hit there, and then we have an angular distribution which depends on Rutherford scattering, and at the same time we reduce the background of our gamma ray spectrum. Here is a typical simulation which may take 3-4 weeks to run in our computers with 200 by 200. This is the one we published recently in Craig Mell's paper. And we have a nice room with good computers to run whatever we need, sorting data analysis, minimizations, and we can actually have, we also have some lectures there. Here we have David Jenkins, who actually is the PI in the UK. For most of the funding come from the STFC through global funding. Now we also got more funding, because once you perform and you achieve things, it's easier to be recognized. And then we got another 10 million rands for what is called Physica. It's a new project where we have other countries in Africa also being involved, and they will come here to be trained, and together with the University of Pretoria, University of York, and the University of Zululand. So we have Ghana, I think, is involved. We have Tanzania, we have Rwanda. All these different countries are involved. We are going to welcome them to train them for some time in getting the knowledge on how to do this quantum technology. So also, from time to time, we have the hobby, and we have some people from NASA and the University of Virginia coming to UWC. We were donated a telescope with, this is a 0.5 meter telescope. It costs like 10 million rands. So it's a portable telescope with Wi-Fi, with GPS, so we can bring it anywhere we want to. And, if Pluto is going up there, if Pluto is crossing our skies, like it happened last year at Uppington in the Northern Cape, we have to go there and we have to wait for Pluto to be right on top for us to measure the occultation of Pluto through a star in the background. And by doing that, we can actually see, depending on the refraction of the light, we can see whether the atmosphere is freezing, sorry, after Pluto going away, is moving away from the sun, or not, right? This is the key of this occultation. There are other kind of occultation. Last month, we did one for an asteroid, and this was to one of the main belt asteroids, just to measure the shape, like we do for nuclei. We also have a bunch of telescopes aligned here, put it there, just so we can measure the shape of the asteroid and check the orbit precisely, right? This is part of the Emirates mission, and we were also contributing to that. So also NITheCS play a role at the beginning of when NITheCS started. We got a little bit of funding from them, and we started building our GitHub, which has now over 58 repositories to deal with big data of different sorts. We have different scan of matrix elements, GM4 scintillator. This is to see what happened with the plastic scintillators, the COVID-19 that was done during also a school here at NITheCS. We have different repositories, 58 for dealing with this big data, and so our students have an easy way to get into doing the physics. This was maintained by Nikita Bernia, Dr. Bernia, who is now in Madrid, the University of Compostela, I mean the Complutense de Madrid, and she's working at CERN. So now let's move to the what is the many body problem? And the many body problem, as you know, we have a Hamiltonian, we have the kinetic term, we have the two nucleon force given here, right? And then we have three nucleon forces, and we have potentials which are different. You know, we don't have the right potential. We don't know the correct potential for the nucleon force, for the nuclear force. So we have to, there are a bunch of them, and it depends on lately what the potential that we normally use are the chiral, based on chiral effective field theory, and because it has a perturbative method which deals with the different nuclear forces in a hierarchical way. So as said by Greiger and Arum, we are dealing with a system of particles, nuclear physics, whose number is neither small enough to allow direct solutions through the Schrödinger equation, for instance, nor large enough to make statistical methods highly accurate, and which interacts through an interaction which has not been pinned down to any definite form. The challenge is to reach numerical convergence of physical observables in the infinite dimensional Hilbert space. And for this, we normally need an effective interaction defined by a model space. As you can see here now, that's the typical problem that we are facing. We have lots of combinations of particles interacting with this one, with that one, and this goes exponentially with the binomial theorem. And, you know, you can go up to 10 to the 10, 10 to the 12. You know, that's the maximal dimension that we can use through diagonalization approaches like the Langsos algorithm or other methods through green function Monte Carlo. So this is the way we can actually tackle the problem, but it's limited. Although I've been told that quantum computers can be an asset to the many body problem, I don't know how far they can go in this mathematical issue. So nuclear physics in particular has been, there's a lot of work being done. As I think was Hans Bethe in 1953 said that there was the biggest problem in history of humankind in terms of the time that was invested in trying to solve the nature of the nuclear force. And according to Mac Goldberger in Caltech, he was at that time quite upset. As you can see, there are a few problems in modern theoretical physics which have attracted more attention than that of trying to determine the fundamental interaction between two nucleons. It is also true that scarcely ever has the world of physics owed so little to so many. So this was a little bit rough, but expressed in a direct way what was happening then, and to some degree what is happening even now. In general, in surveying the field, one is oppressed by the unbelievable confusion and conflict that exists. It is hard to believe that many of the authors are talking about the same problem, or in fact, that they know what the problem is. So there's a huge amount of data which remains to be remains unexplained. As you go to the National Nuclear Data Center in Brookhaven, but this has branches all over the world, you can actually look at the data which is available, and you have a lot, which is not easy to explain even nowadays. This is the man who has done a lot of work, 148 evaluations in nuclear data sheets. So most of this data set come partly by this guy here, by Barra Singh. And recently we just published a memory in the atomic data and nuclear data tables in search of truth, where we expose his, we celebrate his scientific achievements. So we have supercomputers with over 1 million microprocessors, 54 trillion mathematical calculations per second. That's the Jaguar, but the Frontier is the new one at Oak Ridge National Laboratory. Progress, as I say here, is linked to better supercomputer technology and new algorithms. We have Bayesian statistics coming very strong. Plausible reasoning from new data. So basically, you need the context of that. You need to know what's happening to keep improving your prediction. And this is something that we normally have to run for many, many days, depending on how heavy the nucleus is. This is a transition probability between one nuclear state to the next. And it's difficult, it's easy to measure, but it's difficult to compute. So electromagnetic transitions provide a stringent test of the many-body Hamiltonian, and this is what we really need, because you can see through the electric operator, electric quadrupole operator, they involve the overlap between the wave functions. This is the final wave function and the initial wave function, right? So this is very important, and this is why, in particular, we want the GAMKA, because with this angular coverage, we can always measure lifetimes, measure the Doppler effect at different angles. So this, for you to understand the situation of the many-body problem, this is the corner here. This is the nuclear shard. Goes to bismuth, lead, and heavy element thorium, thorium, radium, radon, all the heavy elements here. But we can only calculate this little corner there, right? So these are the typical dimensions according to the binomial theory that you have to deal with, and this is probably the best we can do to solve it from first principles ab initio. Is oxygen 18, nothing else. The rest has to be, we need to play little tricks, density functional, different cluster models, or whatever is the case. We need to play some truncations and some renormalizations to try to access some calculations for these guys to get some predictions. Here is the only place where the Schrodinger equation can be solved according to the dimensions that we have. Further, as the nucleus becomes heavier, things become more complicated. So around 2025, I finished my PhD then, and there was some exciting news about how accurate the excitation energies were predicted by adding 3 nucleon forces to the 2 nucleon forces, right? And then it was very interesting to see, for instance, that the predictions, as you can see here in the case of beryllium-10, this blue is 2 nucleon force, and this yellow is 2 nucleon plus 3 nucleon forces. This is the argon V18, and this is the Illinois 2, different versions, the Illinois 7, whatever. And you have, for the 2 nucleon force, you have the first 2 plus here, but as you add the 3 nucleon force, this first 2 plus actually change order and goes here. And this second 2 plus, which was the second 2 plus, goes down to a lower energy. So there was an inversion of the states if you added 3 nucleon forces, which was very important to understand at that time if it was real or not. So also there was the thing that this guy here should have a negative quadrupole moment, should be prolate in shape, and this guy going up with the 3 nucleon forces should be oblate in shape. So there was a lot of things that needed to be tested experimentally, and that's what we did. And here you have a typical, this is actually chiral effective field theory, different leading orders. As you can see, the hierarchy of the nuclear forces, 2 nucleon forces, 2 nucleon forces. At the next leading order, you have 3 nucleon force. At the next leading order, you have 4 nucleon forces. But these are very difficult to calculate, all these contacts. So we basically have these up to some point here. The rest is very difficult to calculate. I mean, all these contacts, all these different, we can apply a perturbation theory because we have constrained the problem. We have renormalized the problem to the degrees of freedom, which are only proton and neutrons, right? And we are not into the quark system anymore. So we just say, okay, there's a big difference in energy between the quarks and the nuclear physics. So that's going to be our separation. We do a integrate out. We cut off the space in a way that there's a lot of physics which we cut off and we don't know whether it's important. But this is the typical picture of getting nuclear forces from chiral effective field theory. So this is the process that the method, experimental method that we prefer to test all these questions arising from the many-body problem. And you have a typical interaction here between incoming beam, and you have a target here. You have the chamber in the middle, and you have this detector arrays, like we have GAMKA. In this case, they are mini ball detectors at CERN. But you can have the same picture here at the iThemba labs as we're going to run this Wednesday. And you have a silicon detector with all these rings where we can actually measure the angular distribution. And as you can see, depending on the shape, you may have a prolate shape or an oblate one. And this is the Rutherford cross-section. The area of those peaks that we are measuring will be in first order, proportional to the transition probability, which I mentioned before, the B2 value, which was given here, right? That transition probability, which measures the overlaps between the wave functions. And you have second order effects, which is the quadrupole moment. Is basically how quadrupole deformed the nucleus is. And that will be a second order effect, which is what we want to measure. We want to measure the first order and also the second order. So obviously, if you go in this angular range, you are very insensitive to the second order. But you open up and you go to large angles, backscatter angles, as we run our experiments, we are more sensitive to these deformations, of these nuclear deformations. So, as I say here, both projectile and target experience strong time-dependent field gradients, which leads to a change in the Coulomb-excitation cross-section here as a function of theta, scattering angle, that depends on the nuclear deformation. So this is the array that we ran the experiments at Triumph. And there was a beautiful array, a picture of my setup. It was the first experiment run with this setup, this particular setup with double-sided silicon detectors at forward and backward angles. And we have 8 of these large gamma ray detectors, which has very high efficiency compared to normal detectors, and allow us to measure the high-lying states in beryllium-10 and carbon-12. I changed the angular coverage to be able to measure the quadrupole shape, the quadrupole deformation of these nuclei. And we're going to see here the results as predicted by the 3 nucleon forces. We have this is negative side is prolate. That's what it was predicted by the argon V18 and the Illinois 2 interaction. And we concluded that this was okay. So we concluded that actually the 3 nucleon forces was relevant. Or actually, we just say that the shape of the nucleus was prolate. If it's positive, it will be oblate, like a lentil shape. This was prolate is like a rugby ball shape. So basically, we run the experiment, and you have the typical, these matrix elements are computed through couple channel calculations, series of couple channel calculations, which are difficult it takes lots of time to match the experimental data to those matrix elements that we have. And it takes also a long time to get this peak in such a beautiful manner. It took me 3-4 weeks, 3-4 months actually, to get this peak to this point, because you need to Doppler correct it, right? So you have nothing. In principle, you have nothing. It's everything in the background. So only when you Doppler correct, you can see this nice peak here, and we can extract the physics, right? So this is how you get things done, trying everything possible, because most of the things were correct. But in this particular case, what has to be done was to rotate the silicon detector by 90 degrees. So the theta, no, the phi angle was correct, and making the right Doppler correction, because otherwise you cannot get this nice peak. It will be always all in the background. So this was only possible thanks to that Tigris array, because it could it has a very high efficiency, which allow us to measure these states, which were 3.3 MeV, 4.4 MeV, and allow us to determine the quadrupole moment and a deeper understanding of the contributions of the 2-nucleon and 3-nucleon potential to the nuclear spin-orbit interaction. So basically, we understood a little bit better what the interaction looks like. So it was published in as Rapid Communication in Physical Review C, and the referee complained, the only complaint was that we didn't have enough data to run the experiment a little bit longer. You know, if we would have run the experiment another week, another 5 days, this could have been easily a physical review letters. However, you know, in these radioactive ion beam facilities, time is very competitive, and you cannot run for as much time as you want. So this was the case. But you know, sometimes you need to run. You need to know what you want, and you need to know that you are doing the right thing, because this would have been a very beautiful physical review letters. This is a physics letters B that was coming from the carbon-12 experiment that we also ran there. It was analyzed by Kumar Raju here at UWC. He came from India, and we measured the shape of life, which was predicted to be oblate, again like the lentil shape, and we actually measured that in particular very oblate shape here. As you can see, the crossing between lifetime measurements and the Coulomb-excitation lies in this one. I will show a minimization later. But it was clear that the shape of carbon-12 was different to beryllium-10, which was lying on this side. So this also was a very beautiful experiment combined with theory. Again, we did the first calculation of the dipole polarizability using first principles. And this was very complicated at that time. It was the first time that was done. And we ran other experiments, related experiments. This one is at CERN here, and at High Solde. This is the particular setup at High Solde. This is the one in Munich, only particle detectors here. And this is the one at Triumph with the double-sided silicon detectors. As the beam comes this way, the beam gets scattered and also goes back and forth. And you know, we went to CERN, and basically we ran with the collaboration these experiments. I was very proud that most of the students, you know, are here also. Craig, Mavella, they ran the experiment there. Here we have Mavella is here, and Craig is here at the back. You know, they have been trained in this group for many years. So, and they are well prepared for action. So then we have this work recently by the experiment that we ran in Munich, in Germany, where we actually have a more precise measurement of carbon-12, because this one was done with 10 to the 11 ions per second. The previous ones was 10 to the 8. And the reason why, because silicon detectors are easy to destroy by the Rutherford scattering. So we cannot just hit them too hard, otherwise we'll kill them, and they cost $10,000, right, each of those. So it's very expensive. So we went to Munich, where we have a gas target. We have different, it's not silicon detectors, so we can run for higher statistics, and that's what we did with this experiment that Sebo just submitted to Physics Letters B. As it comes out, excellent news. Thanks for the update. Now we know what to do for the next years, because any ab initio calculation didn't predict, as you can see here, they came short from the weighted average, which is 0.09 EV. It's a very elongated oblate shape. And these ab initio calculations with any of those interactions, they are missing the clustering part of the interaction. And only, I believe, if you add that clustering part, maybe or may not be, you have to test it, you will be able to predict or calculate the right quadrupole moment. So all the experiments being done, and they all agree with a large quadrupole moment for the for carbon-12, the nucleus of life, as we call it. So a little introduction here. Just I mentioned GAMKA before. We have built a pipeline of new kind of experiments. I'm telling you these experiments, but you know, I will show you now what we did here at the iThemba labs. But the goal was to create something similar to whatever they have in Argonne National Laboratory here in Ganil in France, or Legnaro in Italy, Canada, or this in Michigan State University. So we wanted to build something similar, which will make us competitive worldwide. We wanted to be the best. There was nothing minor than being the best, competitive, and running experiments that no one can ever do before. For that, we developed new things, new techniques, and we ran different kind of experiments where, I'm going to explain a little bit later, we were more sensitive to those second-order effects than we are in other places. So this was a huge pipeline built with colleagues at the iThemba labs, and with mostly is our team here again. Craig is here, Mabella is there, Elias didn't come today, and Kenzo went for machine learning. Makabata is doing big data in Johannesburg, and this guy here, Kumar Raju, is now an associate professor in India. So we built, actually he also went to China for a postdoc and built something very similar. And we have some experiments with some Chinese collaborators that we are analyzing right now. So this is the setup. We have the old frame with all the Clover detectors. This is not GAMKA, this was before 2016. We have our silicon detectors, preamplifiers, bias supply, high-performing computer. We need to develop sorting codes, GN simulations of what was happening, these Gaussian minimizations of matrix elements, different proposals, experimental proposals elsewhere, requiring beam time, requesting beam time at CERN, at Triumph, at Munich, here at the iThemba labs. You have to keep in mind that these experimental proposals are not done for the faint-hearted. This costs 100,000 US dollars per day, or 100,000 euros per day to run, a minimum. So you need to have a very strong science case for many of these proposals to be accepted internationally. So normally you have international panel that comes here or there, and they decide on the science case. So we have a flexible chamber plus extension plus feed-throughs. I think I'm working on the chamber right here. We need to do new beam development because we wanted to run new nuclear reactions, not the same ones that we have run forever. So we wanted to go and be innovative in every aspect, to try to run something which was entirely different. Also, at that time, colleagues at iThemba developed the data acquisition system, the digital data acquisition system, which was very, very important because we allow us to run experiments without dead time, essentially. So this was the experimental setup, the pipeline to do this kind of particle gamma coincidence measurements. For that, our dream was to get GAMKA plus these state-of-the-art double-sided silicon detectors at backbone angles and measure the second-order effects in Coulomb-excitation perturbation theory. So we did for that GN simulations, and we need to control the whole situation. So this was the Rutherford scattering, and we ran the simulation with the silicon detectors, and this was the MSc, Nicholas Erasmus, and also Kenzo worked on that. And I thought that Craig was working on that paper to get it done. Craig, are you finishing that paper? So an accurate simulation of elastic peaks provides a cleaner particle tagging, high energy calibration points, and a test of experimental conditions such as target thickness. We know what is the target thickness, is very important to know, the beam energy, and linearity of electronic modules. So these are conditions that we need to control 100% when we apply data analysis and we try to extract these quadrupole moments from the cross-section determined here for argon 36. It was our proof of principle experiment at the iThemba labs. It was published in Physical Review C. And as you can see here, when you have a projectile, argon 36, on a heavy target, like platinum 194 in this case, or lead 208, it allows you, because the A of the target is here dividing, allows us to have a higher sensitivity to these measurements of second-order effects. And this was our approach from the beginning. We are going to do that. But for that, we need to have these guys. This guy was easy because argon is a noble gas. You can buy the gas bottle, boom, inject it into the ion source, and run the accelerator. But there were other things that they were not so obvious, right? And we needed to develop those compounds. So pipeline, this is the cluster nucleus as this was neon 20 beams, also on a heavy target. Unique experiment until then, because it was never run like this with a heavy target. Before it was run with unsafe energies, where you have invoke the nuclear force, and then the analysis wasn't very clear of what happened in those experiments. Actually, they were actually not considered after 1970s, 80s. There were experiments in the early 70s, 60s that they were actually disregarded because they were not reliable. So then we ran this experiment with a very safe distance of closest approach between target and projectile. And we did this minimization. It took a year or plus a year to get this thing right, or more. And we got a very nice Doppler correction of, you can see the peak here. The brown thing is without Doppler correction. You can see nothing here. But once you do the Doppler correction, you see the peak of interest. The physics stands up. And this is what we want to measure. And we run calculations. And we see this, the bowling pin nucleus. It's a clustering of alpha particles, 4 alpha particles, as you can see here, which makes a prolate shape in agreement with whatever we calculated here. We calculated, or we determined actually. The first, we measure the most accurate quadrupole moment of neon 20 up to date. We wanted to do something more. We wanted to explore more collective excitations, like surface vibrations in nuclei, because there are surface vibrations everywhere in atoms, in molecules, but in nuclei it wasn't so clear, it wasn't so obvious, because there were some papers at that time where I was part of some of the experimental work led by Paul Garrett and John Wood, who come here regularly, and they claimed that there was no such thing as surface vibrations. To have a surface vibration, you need to have a spherical nucleus. I can oscillate about that spherical nucleus. And it follows a very particular pattern of ground state 0, first excitation 2, and then you have 0, 2, 4. 0, 2, 4, 0 phonon, 1 phonon, and 2 phonon excitations. So this typical scheme is seen throughout. You can see another example here. Now this should be like, this should be almost degenerate. So this nickel 60 was a very good example. Nickel 62 and nickel 60. Here, as you can see, things, they don't follow the pattern here and here, because either you have more pairing interactions, or here you have a shape coexistence, a different effect that may play a role and compete with a pure vibrational excitation. But for these particular cases, nickel 60 and nickel 62, they look like they were vibrational, also because the quadrupole moment was almost 0, consistent with 0, which is what you expect for a spherical nucleus. But not only for that, that's what the theory says. So, yeah. So then we had to develop these beams. We had to run this nickel on heavy targets, right? On lead or platinum, to get this second order effect right. So we needed to do this organometallic chemistry, this sandwich molecule where you have the carbons and the hydrogens around. This a sandwich molecule where you have the nickel inside, in the middle. And once you put it into the ion source, you break all these bonds and only you get the nickel. But you need to produce this nickel in enriched manner. You cannot have just natural nickel, because you have 25% or 26% on nickel 30, nickel 60, 24% on nickel 58, 20% on nickel 62, whatever it is the case. So what you need in these particular cases is a pure beams. So pure beams comes at a price. You need to buy the enriched powder, in this case the nickel 60 and the nickel 62, in metallic form. You create this organometallic compound, this sandwich molecule, you inject it into the ion source, and then you can accelerate it with the cyclotron. It took us another few years, another PhD in NITheCS, new laboratories. And again, it was done in a way that we can run new physics in inverse kinematics and study second-order effects in Coulomb-excitation, strength functions, and also lifetimes, because lifetimes, as the nucleus moves faster, the recoil velocity is larger, so the Doppler effect is more pronounced. So we are more sensitive in this kind of reactions in inverse kinematics. So this was what we did here, and the different what happened in the chemistry lab. How do we compound this? We created some tests. We did the Fourier transform, infrared, X-ray diffraction, and everything looks okay. But eventually, we needed to run the experiments, and this is what we had to do. The hard work was this experiment, which we proposed at the iThemba labs to run nickel 60 and nickel 62 on a heavy target. And this is the soccer ball frame, newly developed and manufactured at SAO. Here is the design, where you have a typical, it's like a soccer ball, basically. And you have all the detectors in there. And you opens up and then close it down. And sometimes it doesn't close too good. And we have some issues at the iThemba labs because of that. But here we was when you go run an experiment, you run 24/7. There's no in astronomy you run overnight. There you run 24/7 because the time is given to you. It's very precious, and you may have 4 days. You need to use the full amount if you want to get some nice data. Here you have a new chamber also, particle detectors, double-sided for rings for angular distributions. And you can see here the rings and some of the sectors. For Doppler correction, we close the chamber here. Inside is the silicon detector, and then the beam comes this way. You need to have a plate and a collimator here so you don't kill the detector with a Rutherford. And you have the beam come this way and then scatter back into the detector, and we get all these backscattered particles in coincidence with those gamma rays that we are detecting with the gamma ray detectors. So this was proof of principle as well. First successful delivery of these enriched nickel beams, exotic beams. They were not just natural beams as we normally do. And this was done in 2019, which allow us to search for this lost paradigm of surface vibrations. According to John Wood and Paul Garrett, there's no such thing. And we wanted to investigate in the nickel isotopes to see what happened. And things are, here we have the Doppler corrected, and this is the first, this is the nice peak. This is in Andile's thesis, right, Andile? Is that in your thesis? So that's your master thesis. You did a very nice Doppler correction. You can see the bluish peak here, which is reconstructed into this nice peak here. Once you do a proper Doppler correction. Also, Craig has been involved here. Mavella is also doing this Doppler correction right now. For his sulfur 32. There are different nuclei being analyzed as we speak. And here we have the Doppler correction for the platinum peaks, because now we are also kicking the target. The target comes not at this is like the beam comes at 10% the speed of light. Maybe the target goes out, kicks out of 1 or 2% the speed of light, but also needs to be corrected. And you can see here everything that was predicted, it came into reality. We created the first Coulomb-excitation measurements to measure matrix elements at the iThemba labs. This was the first time worldwide. So this, for those who want to listen, allow an extension to the nuclear reactions program at the iThemba labs, because you can produce through this same method different kind of reactions which were not available until that moment, right? We have put GAMKA pipeline for Coulomb excitations. We have developed new beams for new reactions. We have built everything for you guys to take care of this thing and bring it to the next level, right? But there was something else that was a second order effect in Coulomb excitation perturbation theory. And here we have first was what we call the reorientation effect, where we measure the shape according to the splitting of the magnetic substates. And you have one here, and then the reorientation effect, or how the This is basically the diagonal matrix element, 2 plus E2, 2 plus. But there was another second one which happened through the virtual excitations through what is called the giant dipole resonance. This giant dipole resonance, we have electric dipole, as you can see in the Taylor extension. The electric comes first, the electric dipole, and then the quadrupole comes next. So this was also, although there are virtual excitation, this was also a situation because these virtual excitations can polarize the nucleus, create a torque in a way that you can enhance that quadrupole collectivity, and the nucleus starts rotating through a different process that had to be corrected, right? So different second order effect altogether, which at the beginning for us was just a correction, but that correction became the main physics that we wanted to develop later on. So for this, I had the privilege to work with people like Sir Dennis Wilkinson, Oxford University, who used to come to Triumph every September. We used to have discussions there for this particular effect. And we have published 15 plus, I don't know how many papers on this particular issue. Professor Macasso is here always telling me about these ratios and telling my students how we can improve this by getting an upper limit on these calculations here, but my students don't listen much. I would like to bring it back again to you guys, Craig, Mavella, Andile, Geneva. These are things which are done, but they can be improved by setting mathematics limits here on top. So for instance, we can actually determine precisely what is the ratio of photonuclear excitation, gamma, photoabsorption cross-section for protons and neutrons, which is very important, as you can imagine, in neutron star mergers and how elements are created. We identify an excess on the symmetry energy from giant dipole resonances built on excitations, on excited states. This is all published in the monthly notices of the Royal Astronomical Society. The nuclear photo disintegration also published. Global trends in physical review C. And also we had to develop new equations to get the polarizability of the first excited states in nuclei through very, very heavy calculations where you have like thousands of matrix elements going up, down to the level of interest. So we have done all this. As I say, they are published in all these journals. It's like the Journal of Physics G. This was me and Sebo. Sebo is now working in the nuclear energy in Coburg. Since he's there, we don't have load shedding. Okay. I'm coming. So it was open access, and it was actually most read during a month or two, within the Journal of Physics G. 5 minutes? Or?
Minus 2 minutes.
Minus 2 minutes, okay. So then I keep going a little bit and explaining a little bit things, like this one here, by measuring those shell model calculations of these electric dipole matrix elements up and down. We understood why this happened originally, why this giant dipole resonance has a different symmetry energy. As you go up in excitation, it was clearly because of the off-diagonal matrix elements we combine in the multiplication here, and some of them were negative, whereas for the ground state, you have the square of the matrix elements, which is always so positive. So we have, now comes also some quantum correlations I wanted to explain. I told you it was difficult to make this talk. How many minutes? What is the time now?
Now you have minus 3 minutes.
Okay, give me minus 5 minutes, and then I will be done. So then we have this quantum correlation that we need to infer because we don't understand the nuclear force, as I mentioned before. And we have these sub-shell gaps on sets of collectivity that we infer from the pairing gaps. From the proton and neutron pairing gaps, we use the theory of pairing. And this short paper deserves some attention as using only the simplest data available from the databases. The text pays attention of nuclear physicists to simple regularities of binding energies as functions of proton and neutron numbers in characteristic even nuclei like nickel, cadmium, tin. So basically, by using different approaches, like getting a resonant energy or pairing energy, and another term, which we call here the energy factor. So we could actually reproduce the B2 transition, which I mentioned before. These are the Kayam data points, and this is the experimental work, the black data points. We reproduce them very precisely without having to run these supercomputers, which was the only way to do so. So also, we infer triaxiality by assuming that the nucleus rotates about the 3 axes and assuming that the particles, the rotation follow a rotational flow. And we deduce different ratios which agree with data quite nicely, particularly for this area, this side here, we have more data points. We don't know here what will happen. But we infer how the nucleus becomes triaxial, and most nuclei are indeed triaxial. This happens also from the matrix elements that we can deduce actually from Coulomb-excitation or from lifetime measurements. And just to conclude, this was tough. You know, as I said before, we have lots of publications, 50 million rands to produce new physics here in South Africa. And we opened doors, CERN, first African-led experiment at CERN. So we have opened many doors for you guys, new laboratories here at the University of Zululand, new pipelines, new beams at iThemba labs. I don't mention even the pipeline that we have at SALT with metal poor stars. But this is what I feel like we are not getting, you know, this particular conclusion. What the Spartans told their youngsters when they were growing up, you know, grow up to be yet braver than we. This was written by Ludwig Wolfman, this book, Theoretical Physics and Philosophical Problems. The last thing, I want to just to bring up this book here for our students, our people to understand the approach. I recommend this to be our NITheCS book, René. Monday starts on Saturday, which my chair knows very well. He read it when he was, how many years you were? Have you ever read this book?
Not yet. I haven't read it yet.
Okay, now you have the opportunity. It's a Russian book, you know, by the Strugatsky brothers, Strugatsky, and it tells you the approach of, you know, these guys are working there. It doesn't happen every day, by working there at 10, 11 p.m. anytime. We have the telescope. We go to SALT to run some observations. We have a very dynamic life in our lab. Here is us giving, you know, David Jenkins giving lectures. We have group meetings, and during the vacation holidays, this December, January, actually, I met some of our collaborators in Madrid. So the same as we bring the telescope, we also need to go there to have some fun. Also with Tony Linus Gray from Oxford University, University College London, who I'm giving a talk in about a month's time. Okay, with that, I want to just -5. It's okay. Thank you so much.
Thank you very much. It was indeed a huge amount of material to comprehend, but we have a recording of this lecture. We can go back to it to catch up. Any questions from the audience? Questions or comments?
Hi. Do you agree with John Wood's claim on the surface vibrations? Do you agree with his opinion at this point? Are there measurements to back that claim about the surface vibrations?
Yeah, that's a very good question. You know, so making these kind of statements are negative statements. Right? I don't believe in this. I don't believe in that. But you need to come with something else, right? So until we cannot come with something else, we cannot believe what is believed, right? So you can say, okay, this chair is not blue, this one here. But if we cannot see that chair, you know, you need to provide an alternative. It's yellow, so it's green, right? So it's very easy to be negative, but it's very difficult to be inventive and say, okay, this doesn't exist, but what is the alternative, right?
Thank you.
Any other questions or comments? Do we have any from the online audience?
Good afternoon. For me, I'll be honest, I think I just got exposed to everything today. So I would love to, I think everything is done remotely, yes? When you're doing all of these experiments.
We go on site. We are like.
That's
No-
where
nothing.
I'm a bit concerned, just from curiosity. So if you are looking at the nucleuses of,
Only salt. Salt is done remote. Whatever observation I mentioned briefly. Although this experiment, you have to go there, you need to set up the experiment, you need to propose the experiment, you need to go in front of this committee of super scientists worldwide, so it's a tough thing. It's a tough exercise. You need to write a letter of clarification. You need to stay. I bought a mattress I still have at home, sorry, in my office, to run these simulations of the experiment. So it's a tough thing, and you need to go there to set it up, to run the experiment for that week. So there cannot be no mistakes. So we cannot allow anyone to run the experiment. It's your experiment. So you need to take responsibility 24/7.
oh yeah, that's on my side was just that the moment you try to see or understand the nucleuses of everything with excited, is it? Or Coulomb-excited? With that, I was questioning that if there's so much gamma rays that is emitted in everything, and you're trying to capture the gamma ray to
Right.
do a proper analysis, where is it done? That's
It's very, very good question. And that's why you have a time. It's a coincidence measurement. It's a coincidence measurement because you have the incoming projectile, you have a target, and then the particle scatters, the projectile scatters, and then as it scatters, gamma rays are detected. The nucleus get excited, and then they excite by gamma rays, right? Those gamma rays are detected at the same time as the scattered particles are coming. So by making a time difference, time condition, that you only want those events, a hit on the silicon detector and a hit on the germanium detector, you avoid any radiation. Any radiation is not coming in coincidence with those events, right? By having the silicon detector, you get rid of anything else, which is not in coincidence with the silicon detector. So this is why coincidence measurements are very important. Also with SKA, where you have this, now we have this satellite, how do you call this? Elon Musk satellites, which are affecting the background at SKA, So these things happen, but if you would do a coincidence measurement, you can get rid of Elon Musk's contribution. Is that clear? Is it okay? You understand now?
I understand. When you were saying it, my head was like, do they have spectral signatures? Does it go to that?
So this thing, you have a time window between, say, 300, 400 nanoseconds. So that's why the time is very important here, right? So with that time window, we get rid of anything that is not coming within those events, right? Those events are happening. We have a radio frequency. The being is coming with a particular frequency, with RF frequency, and then you have a timing which is given by that, and that allows us to get this like a clock. We only get those things within that clock. Anything else that is physically there is not going to come and affect us. So that's why you reduce the background quite very, very substantially.
Okay, thank you.
Well, with that, I would like to thank the speaker once again.
Thank you.
And also to present to you this edition of magazine that NITheCS publishes.
Thank you. Thank you so much for
The
the invitation.
managing director is Professor Sophie Marquez. She's one of the NITheCS associates, and she also works here at Stellenbosch University.
Thank you. Thank you so much.
Thank you very much.